Hello everybody and welcome. Today we are going to be talking about water potential. Water potential relates to a couple fundamental concepts in biology that I want you to think about throughout the entirety of this video. So I'm going to write them down over here on the side. These are entropy and movement across membranes. I'm just going to write membrane movement. Okay, so let's get into it. Water potential is a very useful tool in biology that assigns a number, a measurement, to a concept of how likely water is to move from one place to another. Now, if you can remember, the movement of water is usually referred to as osmosis. Before we get into water potential itself, I want to quickly go over osmosis. Osmosis is a great thing to talk about in relation to these two key concepts over here. As for the first, entropy, this isn't a video on entropy, so I'm not going to go into great detail, but I do need to quickly go over it. Fundamentally, all entropy is the concept that in our universe, everything will move from states of high order to disorder. So with osmosis, let's say you poured some water into the corner of this container. So this is the instant after you poured the water in, and all the water is concentrated over here. So we'd say that this is a higher state of order. All the water molecules are organized on this side. What do you predict would happen if you just poured this water into this container and let it be? Well, obviously these water molecules are going to start moving into this open space until it looks something more or less like this. Over here was the high state of order, quite organized, versus this. This is more disorderly, they're not all concentrated on one side, so it's less organized. Another rule about osmosis is that water generally likes to move to where there's other molecules. I remember my teacher used to tell us, water likes to party. Water wants to move to where there's lots of other things to dissolve. And this could sometimes go against common sense. Let me give you an example of what I'm talking about. Say we have this closed container, and here's a membrane here, a barrier, that only water molecules can pass through. So here in blue are these water molecules. Now, on the right side here, there's going to be more water molecules than over here. Let me make this a little more obvious. So, if it was just water on both of these sides, by the basic rules of diffusion, you'd expect a net travel of water molecules from the right to the left until it reached a state of equilibrium. But now here's where it can get tricky. Let's say we introduce some sugar. The water is still free to pass through this membrane, but the sugar can't. There's still more water and more of everything on the right side than the left. So by the basic principle of diffusion, where things flow from high concentration to low, you would expect most of this water to move over here till there was equal amounts. But that's not necessarily the case. It's not just from high concentration to low concentration, and this is the tricky part. It's high concentration of free water molecules. So this is what I'm talking about. Not all of these water molecules are free to move over to this side. If this sugar is dissolved in this solution, then the picture we have really should look more like this, with these water molecules surrounding this sugar, because this is what happens when things dissolve. The difference in polarity causes these water molecules to bond to the outside of this sugar. Now, since the sugar can't pass through this membrane, it means neither can all the water bonded to it. So what you really have to look at is not the concentration of water molecules, but the concentration of free water molecules, or these guys, the ones not bonded to anything. And since there's more on this side than this side, the net flow of water is actually going to move in this direction until there's an equal amount of free water molecules on each the left and the right. So this side, this right side over here, is going to gain water in this whole process of osmosis. This is a little bit confusing, and this is why water potential and the formula can actually be quite a nice tool to use. Another factor that comes into play in the movement of water and liquid is pressure. If you think about holding a water bottle, if you're just holding it, water isn't going to flow out of the water bottle, it's going to stay inside. But if you squeeze it and apply pressure, water's going to move out. So obviously pressure comes into play as well. So the formula for water potential takes this all into consideration. I don't want you to let these symbols and math confuse you, because it's really just a representation of these concepts we talked about. This trident without the subscript over here just stands for water potential. The one with the S here stands for solute potential, which is what we just talked about, where dissolved molecules in water can change the amount of free water molecules, changing the movement of water. And over here, this P stands for pressure potential, which is just like the water bottle that we talked about. So the pressure is going to change the overall water potential and where water wants to flow. So solute potential has its own equation, and I'm going to write it down over here. The equation for solute potential is negative I CRT. I stands for ionization constant. And to explain it, I'll give you an example. Say our solute is basic sugar. So when you dissolve sugar, the water is going to surround it, but it's only this one molecule. When you put in a certain amount of sugar, you're putting it in by these single molecules. And so we would say that the value of I here is just 1. But if you have something else, say sodium chloride or salt, it's going to look like this. And when you dissolve salt, the water doesn't just surround the salt, but it breaks up the two molecules to look like this. So for every molecule of sodium chloride you put in, you don't just put in one thing for the water to surround, there's actually 2. So the ionization constant for sodium chloride would be 2. This C here just stands for concentration, and what this is the amount of solute in your solution in moles per liter. R is what we call the pressure constant, and it's a number that's multiplied in every time, and it's 0.0831, and this is going to be the same in all your equations. And finally, we have T, and this stands for temperature measured in kelvins. Kelvins is just a way we commonly measure temperature in science, and all you have to do to convert from Celsius to kelvins is take your degrees Celsius and add 275 to it, and you'll get your degrees in kelvins. So as you might have noticed, there's a negative sign here. So as you raise any one of these numbers here, I, C, or T, your solute potential is going to get more negative, or it's going to drop. And so when you add it into this equation, your overall water potential is going to go down. And just like diffusion, water potential goes from higher potential to lower. So the lower your number is, the more likely water is going to flow to that area. And we measure all this in bars. So let's say we have a beaker with a cell in it, and it's in pure water. So this means the water potential of the beaker equals 0 bars. And say the cell, it has a negative 5 bars. Water is going to flow from the beaker to inside the cell here, because it's going to go from higher down to lower. Solute potential is much more confusing than pressure potential. The pressure potential is usually going to be given to you. It's just the pressure on a closed container measured in bars. So if you have an open beaker, the pressure potential is always going to equal 0 for that beaker. But if you have a closed cell, your pressure potential is going to equal something else. That was a quick video on water potential. Remember the big ideas, and thanks for watching.